Right now, as you watch this video, you are sitting at the center of the observable universe. From your perspective, galaxies stretch away in every direction for 46.5 billion light-years, creating a perfect sphere of cosmic structure with you at its exact center. This seems to confirm what humans have intuitively believed for millennia, that we occupy a special, central position in cosmic architecture, that there must be some cosmic downtown, some universal center of mass around which everything else revolves. We were catastrophically wrong. The universe has no center. Not just no center that we can find, but no center at all. Not in any direction, not at any location, not even in principle. This isn't a limitation of our current knowledge or technology. It's a fundamental feature of reality so counterintuitive that it challenges our most basic understanding of space, structure, and our place within existence itself. What if I told you that the observable universe centered on you is completely identical to the observable universe centered on an alien observer in a galaxy 10 billion light-years away? That every point in space can equally claim to be the center of the universe because the concept of cosmic center literally has no meaning? That the very question, where is the center of the universe, is as meaningless as asking, what does purple taste like? Or, how much does a thought weigh? The discovery that the universe is centerless represents one of the most profound revelations in human history. More shocking than learning the Earth orbits the Sun, more disorienting than discovering quantum mechanics, more philosophically devastating than realizing time is relative. It forces us to abandon not just geocentrism or even heliocentrism, but any form of centrism whatsoever, revealing a cosmos so alien to human intuition that our language barely contains concepts to describe it. This centerlessness emerges from the fundamental geometry of expanding space itself. The universe isn't expanding into some pre-existing void with empty space at its edges and a dense center where expansion began. Instead, space itself is expanding everywhere simultaneously, carrying galaxies along like raisins in rising bread dough. Every point in space sees every other point moving away from it, creating the illusion that you're at the center when actually there is no center to be at. The mathematical framework describing this centerless expansion comes from Einstein's general relativity, combined with careful observations of distant galaxies that reveal the same cosmic expansion pattern, regardless of which direction we look. The Hubble constant, the rate at which space expands, is the same in every direction, creating a cosmic expansion that is homogeneous and isotropic on the largest scales, with no preferred location or direction. But this uniformity itself seems impossible. How can the universe look exactly the same in every direction if there is no cosmic center organizing this structure? How can galaxies 26 billion light-years apart on opposite sides of our observable universe have nearly identical temperatures and densities when they've never been in causal contact with each other? How can cosmic expansion be so perfectly coordinated across distances far larger than light could have traveled since the Big Bang? The resolution involves cosmic inflation, a period in the universe as first fraction of a second when space expanded exponentially, stretching quantum fluctuations to cosmic scales while maintaining perfect homogeneity. This inflation didn't happen at some central location and spread outward. It happened everywhere simultaneously, creating the centerless expansion we observe today while solving the horizon problem that would otherwise make cosmic uniformity impossible. Recent observations have pushed our understanding of cosmic centerlessness to extraordinary precision. The cosmic microwave background radiation, the afterglow of the Big Bang, shows temperature variations of only 10 parts per million across the entire sky, confirming that the early universe was homogeneous to incredible precision. Dark energy surveys mapping billions of galaxies reveal large-scale structure that is statistically identical in every direction, with no evidence for any cosmic center or preferred location. But the implications extend far beyond astronomy into philosophy, consciousness, and the meaning of existence itself. If the universe truly has no center, what does this mean for our sense of place and significance? How do we understand direction, location, and cosmic geography in a centerless reality? What does it mean to exist when existence itself has no fixed reference point? The psychological impact of cosmic centerlessness cannot be overstated. Humans evolved to navigate environments with clear spatial hierarchies, landmarks, territories, centers of activity that provide orientation and meaning. Our intuitive understanding of space assumes centers, edges, insides and outsides, up and down directions that make sense within local gravitational fields. But the cosmos operates according to geometries that transcend these evolved intuitions completely. This centerless universe contains mysteries that challenge every assumption about cosmic architecture. Dark matter comprises 27% of cosmic density, but interacts only gravitationally, creating invisible scaffolding for galaxy formation without revealing where this cosmic construction might be centered. Dark energy, making up 68% of the universe, drives accelerating expansion that appears perfectly uniform across all directions and distances, suggesting that whatever force dominates cosmic evolution operates without any center of influence. Tonight, we're going to explore how human understanding evolved from placing Earth at the cosmic center through the Copernican revolution that displaced us from the center of the solar system, to the modern revelation that the universe itself has no center whatsoever. We'll discover how careful observations of galaxy recession velocities revealed cosmic expansion, how Einstein's equations predicted centerless geometries before observations confirmed them, and how modern cosmology has verified this centerlessness to extraordinary precision. You'll understand why the question, "What is the universe expanding into?" fundamentally misunderstands the nature of cosmic expansion, how cosmic inflation created perfect centerlessness through exponential space expansion, and why every location in the universe can equally claim to be the cosmic center because no such center exists. We'll explore how dark energy maintains this centerless expansion against gravitational collapse, and what cosmic centerlessness might mean for the possibility of multiverses, infinite space, and the ultimate fate of existence itself. We'll journey from ancient geocentric models through medieval cosmology to modern observations that have definitively established that we live in a universe where the very concept of center has no meaning. Not because we haven't found it yet, but because the mathematical structure of reality makes cosmic centers impossible. You'll discover why this centerlessness might be the most important fact about existence, and how it transforms every question about our place in the cosmos. If you're fascinated by the mind-bending possibility that the universe has no center, that every location is equally central and equally peripheral, and that our cosmic address has no fixed reference point in an infinite centerless expanse, subscribe and hit thumbs up. And here is a question that takes on new meaning in a centerless cosmos. If there is no cosmic center to be special, no universal downtown where the action happens, does this make every location in the universe equally significant, or does it make significance itself meaningless? Comment below. I'll pin the most thoughtful answer, because in a centerless universe, every perspective might be equally valid. But we're getting ahead of ourselves. To understand how we discovered the universe has no center, we first need to understand how deeply the assumption of cosmic centers is embedded in human thinking, and how revolutionary the idea of centerlessness really is. Now, let's begin this journey to the edge of human understanding, where we'll discover that the universe is stranger, more uniform, and more fundamentally democratic than we ever imagined possible. Chapter 1. The intuition of centers. Human consciousness evolved within environments where centers dominate spatial organization, from the campfire around which social life revolves to the hierarchical territories that define tribal boundaries. This evolutionary heritage creates powerful intuitions about spatial structure that assume every meaningful space must have a center, an organizing principle that determines relationships between all other locations. Understanding how deeply these center-based intuitions are embedded in human thinking reveals why discovering cosmic centerlessness required such a radical revolution in our understanding of space itself. The psychological foundation for assuming cosmic centers begins with the way consciousness constructs spatial experience. Every conscious observer naturally places themselves at the center of their perceptual world, with sensory information radiating inward from a spherical boundary defined by the horizon of sight, sound, and touch. This egocentric spatial framework creates the immediate impression that awareness itself occupies a privileged central position within sensory space, making self-centered perspectives feel like fundamental features of reality rather than artifacts of neural information processing. This personal centrality extends automatically to cultural and cosmic scales through processes that anthropologists recognize as universal human tendencies. Every human culture places itself at the center of moral, geographic, and often cosmic significance, creating worldviews where our territory, our people, and our cosmic environment occupy the most important central positions. These cultural geocentrisms reflect deep cognitive biases that make self-centered thinking feel natural and objective rather than perspectival and constructed. Ancient cosmologies universally reflected these center-based intuitions by placing human habitation at the center of cosmic structure. Egyptian cosmology positioned the Nile Valley at the center of a flat Earth surrounded by cosmic waters. Mesopotamian models placed their cities at the center of circular Earth disks floating within cosmic spheres. Chinese cosmology positioned the Middle Kingdom at the center of a square Earth beneath a circular heaven. These diverse cultures independently developed center-based cosmologies because center-based thinking feels psychologically inevitable. The Greek development of systematic astronomy and geometry provided sophisticated mathematical frameworks or center-based cosmologies that appeared to confirm intuitive expectations through rigorous observation and calculation. Aristotelian cosmology placed Earth at the center of nested celestial spheres, with the moon, sun, planets, and stars orbiting in perfect circles around the central terrestrial realm. This geocentric model explained astronomical observations while satisfying psychological needs for cosmic centrality and mathematical elegance. Ptolemaic astronomy refined geocentric models through epicycles and mathematical techniques that achieved remarkable predictive accuracy for planetary motions while maintaining Earth's central position. The Ptolemaic system's ability to predict eclipses, planetary positions, and seasonal changes provided empirical support for geocentric assumptions that seemed to confirm humanity's central cosmic significance. These mathematical successes made geocentrism appear scientifically validated rather than merely intuitive. Medieval cosmology integrated Aristotelian geocentrism with religious frameworks that provided theological justification for human cosmic centrality. Christian cosmology placed Earth at the center of creation as the stage where divine drama unfolds, with celestial spheres surrounding the central terrestrial realm where moral choices determine eternal destinies. Islamic cosmology similarly positioned human habitation at the cosmic center, while medieval Jewish thought placed Jerusalem at the center of Earth and Earth at the center of creation. These religious geocentric models served psychological functions beyond astronomical explanation by providing cosmic validation for human significance and moral responsibility. If humans occupy the central position in cosmic architecture, then human choices and spiritual development become cosmically important rather than peripheral accidents. Geocentric cosmologies thus supported religious worldviews by making human existence central to cosmic purpose and meaning. The aesthetic and philosophical appeal of cosmic centers extends beyond religious considerations to mathematical beauty and logical necessity. Center-based structures appear more elegant and comprehensible than centerless alternatives, providing clear reference points for understanding relationships, distances, and directions. Mathematical systems with central organizing principles enable cleaner geometric relationships and more intuitive calculations than systems without natural centers or universal reference frames. This aesthetic preference for centered structures influences scientific thinking even today, creating subtle biases toward theoretical frameworks that preserve some form of cosmic centrality or special reference frames. The search for fundamental particles, universal constants, and privileged coordinate systems reflects lingering assumptions that reality must have central organizing principles discoverable through scientific investigation, even when empirical evidence points toward more democratic distributions of cosmic significance. The transition from geocentric to heliocentric cosmology represented humanity's first major confrontation with cosmic decentering, but it preserved center-based thinking by simply relocating the cosmic center from Earth to the Sun. Copernican heliocentrism displaced human habitation from the cosmic center, while maintaining the assumption that cosmic structure must have some central organizing principle. This preservation of cosmic centrality made heliocentrism psychologically manageable despite its revolutionary implications for human significance. Even post-Copernican astronomy continued assuming that the solar system occupied a central, or at least special, position within stellar arrangements. Early telescopic observations revealed that stars have different brightnesses and distributions, but these observations were interpreted within frameworks that assumed our stellar neighborhood must occupy some privileged location within galactic structure. The possibility that stellar arrangements might be uniform and centerless seemed too psychologically alien to consider seriously. The discovery that the Milky Way is a galaxy among billions of others represented another decentering revolution, but it still preserved assumptions about cosmic hierarchy and central organization. Early galaxy catalogs were interpreted as revealing galactic clusters with central dominant galaxies surrounded by satellite systems, maintaining the intuitive expectation that cosmic structure must organize itself around gravitational centers and hierarchical relationships. Modern cosmology as revelation that the universe has no center represents the ultimate challenge to center-based intuitions because it eliminates not just human centrality or solar centrality or galactic centrality, but the very concept of cosmic centrality itself. This complete abandonment of center-based thinking requires psychological adjustments that go far beyond previous decentering revolutions because it challenges the fundamental spatial categories through which consciousness organizes experience. The difficulty of accepting cosmic centerlessness appears in persistent misconceptions that treat the Big Bang as an explosion that occurred at some central location and spread outward through pre-existing space. This explosion analogy preserves center-based thinking by imagining cosmic expansion as emanating from an initial central point, even though the actual Big Bang represents the simultaneous appearance of space everywhere without any central point of origin. Understanding cosmic centerlessness requires developing new spatial intuitions that transcend evolved psychological tendencies towards center-based thinking. This cognitive revolution involves recognizing that mathematical relationships can exist without central reference points. That expansion can occur without central sources, and that structure can emerge from uniform processes without hierarchical organization around privileged locations. The philosophical implications of truly centerless thinking extend beyond cosmology to questions about consciousness, identity, and meaning in contexts where traditional spatial metaphors lose their organizing power. If consciousness naturally assumes central perspectives, but reality operates according to centerless principles, then subjective experience and objective reality operate according to fundamentally different organizational principles that require careful philosophical analysis to reconcile. But confronting our intuitive need for cosmic centers raises immediate questions about how we actually discovered that the universe is centerless. What observations forced astronomers to abandon center-based cosmologies? How do we observe and measure the properties of space that has no center? What does cosmic expansion look like from the inside when there's no outside perspective from which to view it? Chapter 2. The Great Recession in the 1920s. Astronomer Edwin Hubble made an observation so startling that it forced humanity to completely reimagine the nature of cosmic space. Nearly every galaxy in the universe is moving away from us, and the more distant the galaxy, the faster it recedes. This discovery of cosmic recession initially seemed to place our local galactic neighborhood at the center of a universal expansion, but careful analysis revealed something far more profound and counterintuitive: that every observer throughout the universe sees exactly the same recession pattern, indicating that cosmic expansion has no center whatsoever. Hubble's revolutionary discovery began with painstaking measurements of galaxy distances and velocities using the 100-inch Mount Wilson telescope, then the largest and most powerful astronomical instrument in the world. By observing Cepheid variable stars in nearby galaxies, Hubble could determine accurate distances to these cosmic island universes, while spectroscopic analysis of galactic light revealed their velocities through Doppler shift measurements. The combination of distance and velocity measurements revealed an unexpected pattern that would transform our understanding of cosmic structure. The Doppler effect, familiar from the changing pitch of approaching and receding sirens, affects light waves in ways that reveal the motion of distant objects through systematic shifts in the wavelengths of spectral lines. Light from objects moving away from observers is redshifted toward longer wavelengths, while light from approaching objects is blue-shifted toward shorter wavelengths. When Hubble analyzed the spectra of distant galaxies, he discovered that nearly all of them showed redshifts, indicating that they are moving away from our location in space. More remarkably, Hubble found that galactic recession velocities increase linearly with distance, a relationship now known as Hubble's law. Galaxies twice as far away recede twice as fast. Galaxies 3 times as far away recede 3 times as fast, and so on, creating a perfect mathematical relationship between distance and recession velocity. This linear relationship suggested that cosmic expansion operates according to precise geometric principles, rather than random galactic motions through space. The initial interpretation of Hubble's observations seemed to confirm humanity's special cosmic position by placing our local galactic group at the center of universal expansion. If all galaxies are moving away from us with velocities proportional to their distances, then our location appeared to occupy the special central position from which cosmic expansion emanates. This interpretation preserved center-based thinking while explaining the observed recession pattern through a cosmic explosion model. However, careful theoretical analysis revealed that Hubble's observations are actually inconsistent with any center-based expansion model. If cosmic expansion truly emanated from a central point, then observers at different locations should see different recession patterns depending on their distance from the cosmic center. Observers near the center should see expansion in all directions, while observers far from the center should see galaxies on one side approaching and galaxies on the other side receding. The key insight came from recognizing that Hubble's law produces the same observational pattern for every observer throughout the universe, regardless of their location. This universal consistency requires that cosmic expansion operates without any central point or preferred reference frame. Every observer sees themselves surrounded by receding galaxies with recession velocities proportional to distance, creating the illusion of centrality when actually no central location exists. The mathematical framework for understanding centerless expansion comes from the Robertson-Walker metric, which describes the geometry of homogeneous, isotropic expanding space. In this geometric description, Space itself expands uniformly in all directions and at all locations simultaneously, carrying galaxies along like markers embedded in the expanding spatial fabric. This expanding space model naturally produces Hubble's law for all observers without requiring any cosmic center. The analogy of raisin bread rising in an oven illustrates how centerless expansion creates universal recession patterns. As the bread dough expands, every raisin sees every other raisin moving away, with more distant raisins receding faster than nearby ones. Each raisin can claim to be at the center of the expansion because the expansion occurs throughout the bread dough simultaneously rather than emanating from any central point. Similarly, cosmic expansion occurs throughout space simultaneously rather than spreading outward from a cosmic center. This centerless expansion model makes specific predictions that have been confirmed through increasingly precise observations. The cosmic microwave background radiation shows the same. Temperature and statistical properties in every direction to extraordinary precision, confirming that cosmic expansion has maintained homogeneity and isotropy since the universe became transparent to electromagnetic radiation. Large-scale galaxy surveys reveal statistical uniformity in galactic distributions across enormous cosmic volumes, confirming that no cosmic center or preferred direction exists on the largest observable scales. The measurement of cosmic expansion has evolved from Hubble's initial observations to modern precision cosmology using Type Ia supernova, baryon acoustic oscillations, and other standard candles and rulers that enable accurate distance determinations across cosmic time. These measurements have confirmed Hubble's law to extraordinary precision, while revealing that cosmic expansion is actually accelerating due to dark energy's influence, adding another layer of complexity to centerless expansion dynamics. The discovery of cosmic acceleration in 1998 provided additional confirmation of centerless expansion by showing that the acceleration appears uniform across all directions and distances. If cosmic expansion had a center, then acceleration effects should vary depending on direction and distance from that center. Instead, observations reveal perfectly uniform acceleration that operates the same way for all observers throughout the universe, confirming that cosmic expansion and acceleration both operate without central organizing principles. Modern surveys mapping billions of galaxies across enormous cosmic volumes have tested cosmic homogeneity and isotropy to unprecedented precision, consistently finding that the universe appears statistically identical in all directions and in all locations on scales larger than approximately 100 megaparsecs. This cosmological principle of homogeneity and isotropy provides the observational foundation for centerless cosmological models. The largest cosmic structures, galaxy clusters, superclusters, and cosmic filaments organize themselves into patterns that show no evidence for overall cosmic centers or preferred directions. Computer simulations of cosmic structure formation based on centerless expansion models successfully reproduce the observed large-scale structure without requiring any special initial conditions or central organizing principles. Even more remarkably, observations suggest that cosmic expansion extends far beyond our observable universe horizon, with space continuing to expand uniformly throughout regions we can never observe. This implies that centerless expansion operates on scales vastly larger than our cosmic neighborhood, making our local observations representative of cosmic expansion operating throughout infinite space. The philosophical implications of cosmic recession without a cosmic center challenge fundamental assumptions about motion, space, and causality. Traditional physics assumes that motion occurs relative to fixed reference frames or central attractors, but cosmic expansion represents motion that occurs without any fixed reference points or central sources. Galaxies recede through expanding space rather than moving through fixed space, creating forms of motion that transcend classical mechanical concepts. This centerless recession also reveals that the universe's past and future cannot be understood through traditional concepts of cosmic evolution, proceeding from central sources toward peripheral regions. Instead, cosmic history unfolds simultaneously throughout all space, with every location experiencing the same evolutionary sequence from hot, dense beginnings toward cold, dilute futures without any temporal hierarchy based on distance from cosmic centers. The measurement techniques that revealed cosmic recession continue to evolve toward even greater precision and longer distance scales. Next-generation telescopes and surveys will map cosmic expansion across larger volumes and further back in cosmic time, testing whether centerless expansion continues to hold at the largest observable scales and earliest cosmic epochs. Future gravitational wave astronomy might provide entirely new ways to measure cosmic expansion through gravitational wave propagation effects, while quantum cosmology theories suggest that centerless expansion might emerge from more fundamental quantum geometric principles that operate at scales far below current observational limits. But understanding the great cosmic recession raises immediate questions about the mechanism driving this centerless expansion. What force or process causes space itself to expand uniformly throughout the universe? How did cosmic expansion begin? And what determines its current rate and future evolution? Why does space expand in ways that preserve perfect homogeneity and isotropy across cosmic scales? Chapter 3. Einstein's Geometric Revolution. Before Einstein, space and time were understood as fixed, absolute stages where physical events unfold. Newton's immutable theater of cosmic drama with absolute positions, absolute simultaneity, and geometric relationships that remain constant throughout the universe. Einstein's general theory of relativity shattered these assumptions by revealing that space and time form a unified dynamic fabric that responds to matter and energy, creating geometries where the very concept of center depends on coordinate choices rather than physical reality. This geometric revolution provided the mathematical framework for understanding how the universe can expand everywhere simultaneously without expanding from anywhere in particular. The conceptual foundation of Einstein's geometric revolution begins with the recognition that gravitational forces can be understood as manifestations of curved space-time geometry rather than forces propagating through flat space. In Einstein's framework, massive objects don't pull on other objects through gravitational forces. Instead, they curve the geometry of space-time itself, and objects follow the straightest possible paths through this curved geometry. This geometric interpretation of gravitation transformed space and time from passive backgrounds into active participants in physical processes. The mathematical description of curved spacetime uses the language of differential geometry, where the properties of space at each point are described by metric tensors that encode information about distances, angles, and curvature. In curved spacetime, concepts like straight line and shortest distance become geometry-dependent rather than absolute, with different geometric backgrounds supporting different notions of spatial and temporal relationships. This mathematical flexibility enables geometric descriptions of cosmic expansion that would be impossible within fixed Newtonian frameworks. Einstein's field equations, relating spacetime curvature to the distribution of matter and energy, admit solutions describing expanding cosmological geometries that have no center or edge. The Friedmann-Lemaitre-Robertson-Walker (FLRW) metric describes homogeneous, isotropic spacetime that expands or contracts uniformly in all directions without any special locations. In this geometric description, cosmic expansion represents the evolution of spatial geometry itself, rather than motion through pre-existing space. The crucial insight is that expanding geometry naturally creates recession patterns that appear centered around every observer without requiring any actual cosmic center. When the scale factor describing spatial geometry increases with time, The proper distance between any 2 points increases proportionally, creating the observed relationship between distance and recession velocity. Every observer sees recession patterns consistent with being at the cosmic center because the geometric expansion operates identically from every spatial location. This geometric interpretation resolves the paradox of how cosmic expansion can appear centered on Earth while actually being centerless. The recession velocities observed from our location represent the local manifestation of global geometric expansion rather than evidence for our central cosmic position. Any observer at any location throughout the universe would observe identical recession patterns because geometric expansion affects all spatial relationships uniformly. Einstein initially resisted cosmological solutions that described expanding or contracting universes, preferring static models that preserve eternal cosmic equilibrium. He introduced the cosmological constant, a hypothetical form of energy that creates repulsive gravitational effects, specifically to enable static cosmological solutions that neither expand nor contract. This modification allowed his field equations to describe stable cosmic geometries that seemed more philosophically satisfying than dynamic alternatives. However, other physicists quickly recognized that Einstein's Weyl equations naturally admit dynamic cosmological solutions without requiring artificial additions like the cosmological constant. Alexander Friedmann derived expanding and contracting cosmological models that satisfied Einstein's original field equations, demonstrating that cosmic evolution represents a natural consequence of general relativity rather than an unwelcome complication requiring special modifications. The geometric expansion described by these cosmological models operates through mechanisms that transcend everyday intuitions about motion and space. Rather than objects moving away from each other through fixed space, cosmic expansion involves space itself growing larger while maintaining its overall geometric properties. Galaxies don't move through space in the conventional sense. Instead, the spatial distances between galaxies increase as the underlying geometry expands. This expansion of space itself explains how cosmic recession can exceed the speed of light without violating special relativity as speed limit. Special relativity constrains the motion of objects through space, but it places no limits on how fast space itself can expand. Sufficiently distant galaxies can recede at velocities exceeding the speed of light because their recession results from geometric expansion rather than motion through space. The geometric framework also explains how cosmic expansion maintains homogeneity. An isotropy, despite appearing to operate faster than light, can travel across cosmic distances. The expansion doesn't need to propagate from place to place like conventional signals. Instead, it represents the simultaneous evolution of spatial geometry throughout all space, according to global geometric principles rather than local causal processes. Modern precision measurements have confirmed Einstein's geometric predictions for cosmic expansion to extraordinary accuracy. Observations of type Ia supernova cosmic microwave background anisotropies and baryon acoustic oscillations all confirm that cosmic geometry evolves according to general relativity's field equations, with parameters determined by the universe's matter and energy content rather than arbitrary initial conditions. The discovery of cosmic acceleration in 1998 provided dramatic confirmation of general relativity's geometric framework by revealing that cosmic expansion is speeding up rather than slowing down as expected from gravitational deceleration. This acceleration requires additional energy components beyond ordinary matter and radiation, dark energy that creates repulsive gravitational effects similar to Einstein's original cosmological constant. Dark energy's uniform distribution throughout space maintains the geometric expansion homogeneity and isotropy while accelerating cosmic evolution toward increasingly rapid expansion rates. Current observations suggest that dark energy comprises approximately 68% of the universe's total energy density, making it the dominant component driving contemporary cosmic expansion while preserving the centerless geometric properties predicted by Einstein's equations. The geometric interpretation of cosmic expansion also predicts the existence of cosmic horizons, limiting distances beyond which objects cannot be observed due to the finite time available for light to travel since the universe became transparent. These horizons represent geometric features of expanding spacetime rather than physical boundaries, with different observers having different but equally valid cosmic horizons depending on their location and the expansion history. Future cosmic evolution, according to Einstein's geometric framework, depends on the universe's total energy density and the properties of dark energy. If dark energy continues driving accelerated expansion, then cosmic geometry will evolve toward exponentially increasing scale factors that eventually separate all galactic structures beyond mutual observational contact. This geometric isolation would create cosmic loneliness on unprecedented scales while maintaining perfect homogeneity throughout infinite expanding space. Alternative cosmic geometries permitted by Einstein's field equations include closed universes that eventually stop expanding and recollapse, open universes that expand forever while decelerating, and flat universes that expand forever while approaching static configurations. Each geometric possibility corresponds to different relationships between the universe's energy, density, and the critical density required for specific cosmic curvatures. The quantum mechanical extensions of Einstein's geometric framework suggest that cosmic expansion might emerge from more fundamental quantum geometric processes operating at microscopic scales. Quantum field theory in curved spacetime predicts particle production, vacuum fluctuations, and other quantum effects that might influence cosmic expansion through back-reaction effects that modify classical geometric evolution. String theory and other approaches to quantum gravity propose that spacetime geometry itself might be emergent from more basic quantum mechanical structures, potentially explaining why cosmic expansion operates according to geometric principles that preserve homogeneity and isotropy. These quantum geometric theories might ultimately explain why the universe has the specific geometric properties that make centerless expansion possible. But Einstein's geometric revolution raises fundamental questions about the relationship between mathematical descriptions and physical reality. If cosmic expansion represents geometric evolution rather than conventional motion, what does this tell us about the nature of space itself? How do we understand physical existence within geometric frameworks that treat space and time as dynamic rather than fixed? What does centerless geometric expansion mean for our understanding of cosmic causality and the relationships between events separated by cosmic distances? Chapter 4. The Cosmic Microwave Echo in 1965. Two Bell Laboratory engineers accidentally detected the most important echo in cosmic history, a faint radiation bath that fills every cubic centimeter of space with nearly uniform thermal energy left over from the Big Bang itself. This cosmic microwave background radiation provides the most direct evidence that the universe has no center, revealing temperature patterns that are statistically identical in every direction to extraordinary precision while encoding information about cosmic geometry that definitively confirms centerless expansion operating according to precisely determined cosmic parameters. The discovery of the cosmic microwave background began as an engineering problem rather than a cosmological investigation. Arno Penzias and Robert Wilson were calibrating a sensitive horn antenna designed for satellite communications when they detected persistent microwave noise that appeared to come from all directions with equal intensity. After eliminating all possible terrestrial sources, including the famous white dielectric material deposited by pigeons nesting in the antenna, they realized they had detected primordial radiation from the early universe. The theoretical prediction of cosmic microwave background radiation had been made decades earlier by George Gamow, Ralph Alpher, and Robert Herman, who recognized that a hot, dense early universe would emit thermal radiation that would cool and redshift as cosmic expansion stretched its wavelengths. By the time this primordial radiation reached the present epoch, it should appear as microwave radiation with a characteristic blackbody spectrum corresponding to a temperature of approximately 2.7 Kelvin. The cosmic microwave background represents a direct observation of the universe as it appeared approximately 380,000 years after the Big Bang, when expanding space had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. Before this recombination epoch, the universe was opaque to electromagnetic radiation because free electrons scattered photons efficiently. After recombination, space became transparent, allowing thermal radiation to propagate freely through the universe for the first time. This cosmic snapshot reveals the universe at its moment of transparency with unprecedented uniformity. The temperature of cosmic microwave background radiation varies by only about 10 parts per million across the entire sky, demonstrating that the early universe possessed nearly perfect homogeneity and isotropy. This extraordinary uniformity provides direct evidence that cosmic expansion operates without any central organizing principles or preferred directions. The precision measurements of cosmic microwave background temperature and polarization patterns have revolutionized cosmology by providing detailed information about cosmic geometry, matter content, and expansion dynamics. The COBE, WMAP, and Planck satellite missions have mapped cosmic microwave background anisotropies with increasing precision, revealing acoustic oscillation patterns that encode information about cosmic parameters with accuracy approaching 1%. These acoustic oscillations represent sound waves propagating through the hot plasma of the early universe, creating compression and rarefaction patterns that became frozen into the cosmic microwave background when the universe became transparent. The angular scales of these acoustic peaks reveal cosmic geometry, whether space is flat, curved, or hyperbolic, while their amplitudes encode information about matter density, dark energy content, and other fundamental cosmic parameters. The acoustic oscillation measurements confirm that cosmic space is flat to extraordinary precision, meaning that parallel lines remain parallel across cosmic distances, and that the geometric expansion operates according to Euclidean geometric principles on the largest scales. This geometric flatness supports centerless expansion models while ruling out closed cosmic geometries that would curve back on themselves or open geometries that would curve hyperbolically. The statistical properties of cosmic microwave background fluctuations provide the statistical properties of cosmic microwave background fluctuations provide the statistical fluctuations provide the strongest evidence for cosmic homogeneity and isotropy by demonstrating that the same statistical patterns appear in every direction across the sky. Power spectrum analysis reveals that fluctuation amplitudes follow Gaussian random distributions with no evidence for special directions, preferred locations, or cosmic centers that would break the statistical uniformity. Even more remarkably, the cosmic microwave background exhibits correlations across angular scales much larger than the cosmic horizon at recombination, creating the famous horizon problem that standard Big Bang cosmology cannot explain. Regions of sky separated by more than 2 degrees show nearly identical temperatures despite being causally disconnected throughout cosmic history preceding recombination. This suggests that cosmic uniformity was established by processes operating before conventional causal mechanisms could coordinate temperatures across cosmic distances. The resolution of the horizon problem requires cosmic inflation, a period of exponential expansion during the universe's first fraction of a second that stretched quantum fluctuations to cosmic scales while maintaining causal connectivity between currently distant regions. Inflation provides a mechanism for creating cosmic uniformity without requiring central coordination, instead achieving homogeneity through quantum mechanical processes operating during exponential expansion. Inflationary models make specific predictions for cosmic microwave background polarization patterns that arise from gravitational wave fluctuations during the inflationary epoch. The detection of these B-mode polarization signatures would provide direct evidence for inflation while confirming that cosmic uniformity results from quantum mechanical processes rather than classical thermal equilibration or central organizing mechanisms. The cosmic microwave background also reveals evidence for dark matter through its influence on acoustic oscillation patterns. The gravitational effects of dark matter modify the propagation of sound waves through the early universe plasma, creating characteristic signatures in temperature and polarization fluctuations that enable precise measurements of dark matter density. These measurements confirm that dark matter comprises approximately 27% of cosmic energy density while being distributed uniformly throughout space. Dark energy's influence appears in cosmic microwave background observations through its effects on cosmic geometry and expansion dynamics. The acoustic oscillation angular scales depend on the distance to the recombination epoch, which depends on cosmic expansion history throughout the intervening time. These geometric measurements confirm that cosmic expansion is accelerating due to dark energy comprising approximately 68% of total cosmic energy density. The combination of cosmic microwave background observations with other cosmological measurements has established a standard model of cosmology, lambda-CDM, that describes cosmic evolution from inflation through the present epoch with unprecedented precision. This model treats cosmic expansion as centralist geometric evolution, governed by Einstein's field equations with specific matter and energy components, determined through observational measurements. Future cosmic microwave background observations will push these measurements to even greater precision while searching for signatures of exotic physics beyond the standard cosmological model. Next-generation experiments will map polarization patterns with sensitivity sufficient to detect inflationary gravitational waves, primordial magnetic fields, and other subtle effects that could reveal new physics operating during cosmic evolution. The cosmic microwave background measurements also constrain alternative cosmological models that attempt to explain cosmic uniformity through mechanisms other than inflation. Steady-state models, cyclic cosmologies, and other alternatives must explain observed cosmic microwave background properties while maintaining consistency with other cosmological observations. Most alternative models struggle to match the extraordinary precision of cosmic microwave background measurements. The philosophical implications of cosmic microwave background uniformity extend beyond cosmology to fundamental questions about the nature of space, time, and cosmic causality. The nearly perfect isotropy suggests that cosmic properties are determined by global principles rather than local processes, raising questions about how cosmic evolution coordinates itself across scales much larger than causal horizons. This cosmic coordination without central control represents one of the deepest mysteries in cosmology, suggesting that cosmic evolution operates according to principles that transcend conventional notions of cause and effect. The universe appears to have achieved nearly perfect uniformity through processes that operate globally rather than locally, implying forms of cosmic organization that may require new theoretical frameworks to understand fully. Modern precision cosmology continues to refine cosmic microwave background measurements while searching for deviations from perfect isotropy that might reveal subtle asymmetries or preferred directions in cosmic structure. Any detection of cosmic anisotropy would revolutionize our understanding of cosmic geometry while potentially revealing new physics operating at cosmic scales. But the cosmic microwave echo raises immediate questions about the mechanisms that created such extraordinary uniformity. How did quantum fluctuations during inflation create the precise patterns observed in cosmic microwave background radiation? What determines the specific acoustic oscillation signatures that encode cosmic parameters? How does cosmic expansion maintain uniformity while allowing local structure formation through gravitational collapse? Chapter 5. The Inflation Revolution in the first 10 to 32 seconds of cosmic existence. Space itself underwent exponential expansion that increased the universe's size by a factor of at least 1026, a process called cosmic inflation that solved multiple cosmological puzzles while creating the nearly perfect uniformity we observe today. This inflationary epoch represents the most dramatic example of centerless expansion ever proposed, where every point in space expanded simultaneously at rates that would make the entire observable universe emerge from regions smaller than elementary particles, establishing the cosmic homogeneity that makes centerless expansion possible. The theoretical motivation for cosmic inflation emerged from attempts to solve fundamental problems with standard Big Bang cosmology that became apparent once precision observations revealed the universe's extraordinary uniformity. The horizon problem asks how regions of space that have never been in causal contact can have nearly identical temperatures and densities. The flatness problem asks why cosmic geometry is so precisely balanced between expansion and recollapse. The monopole problem asks why certain exotic particles predicted by particle physics theories are not observed in cosmic abundance. Alan Guth's original inflationary proposal in 1980 suggested that these problems could be resolved if the early universe underwent a period of exponential expansion driven by a hypothetical scalar field called the inflaton. During inflation, this field would possess nearly constant energy density that creates repulsive gravitational effects, causing space to expand exponentially while maintaining constant energy density through the continuous creation of space and matter from vacuum fluctuations. The mathematical description of inflation uses the framework of scalar field cosmology, where the inflaton field evolves according to quantum field equations in expanding spacetime. When the inflaton field becomes trapped in a metastable vacuum state with high energy density, it drives exponential cosmic expansion through Einstein's field equations. This inflation continues until the field eventually transitions to a lower energy state, ending the exponential expansion phase and beginning conventional cosmic evolution. The key insight is that inflation naturally creates cosmic uniformity without requiring any central coordination or organizing mechanisms. During the exponential expansion phase, quantum fluctuations are stretched from microscopic to cosmic scales while maintaining their statistical properties. Regions that are currently separated by billions of light years originated from causally connected microscopic regions that were in thermal equilibrium before inflation stretched them beyond causal contact. This stretching mechanism explains how cosmic uniformity can exist across scales much larger than the cosmic horizon without requiring faster-than-light information transfer. The uniformity was established during a pre-inflationary phase when currently distant regions were in causal contact, then preserved during inflation as these regions were stretched beyond mutual communication. Inflation thus creates apparent causal correlations through causal processes operating before exponential expansion. The exponential expansion during inflation also naturally explains cosmic flatness by stretching any initial curvature to negligible levels. Just as the surface of a balloon appears flat when expanded to enormous size, cosmic space becomes geometrically flat when expanded by the enormous factors achieved during inflation. This geometric flattening makes cosmic expansion approach the critical balance between expansion and recollapse that we observe today. Inflation also dilutes the density of exotic particles like magnetic monopoles by expanding space so rapidly that their number density becomes negligibly small. Any pre-existing matter or radiation gets diluted to undetectable levels during exponential expansion, leaving only the energy associated with the inflatoned field itself. This explains why we observe a universe dominated by ordinary matter and radiation rather than exotic relics from earlier epochs. The end of inflation occurs when the inflatoned field finally transitions from its metastable vacuum state to a lower energy configuration. This transition, called reheating, converts the inflatoned field's energy into ordinary matter and radiation that becomes the hot, dense plasma described by standard Big Bang cosmology. The timing and dynamics of reheating determine the initial conditions for subsequent cosmic evolution, including nucleosynthesis, structure formation, and radiation decoupling. Modern inflationary models have evolved far beyond Guth's original proposal to include sophisticated treatments of inflatoned field dynamics, quantum fluctuations, and observational predictions. Slow-roll inflation describes scenarios where the inflatoned field evolves gradually down its potential energy curve, creating extended periods of exponential expansion with specific observational signatures in cosmic, microwave background radiation patterns. The quantum fluctuations of the inflatoned field during inflation create the seeds for all subsequent cosmic structure formation. These quantum fluctuations get stretched to cosmic scales during exponential expansion, creating tiny density variations that eventually grow through gravitational collapse to form galaxies, stars, and larger cosmic structures. The statistical properties of these quantum fluctuations determine the observed patterns of cosmic structure throughout the universe. Chaotic inflation, proposed by Andre Linde, suggests that inflation occurs whenever and wherever scalar fields with appropriate potential energy configurations exist in sufficient quantities. This leads to eternal inflation scenarios where inflation continues indefinitely in some regions of space while ending in others, creating infinite collections of causally disconnected cosmic domains with potentially different physical properties. Eternal inflation has profound implications for cosmic centerlessness by suggesting that our observable universe represents just one small region within an infinitely larger inflating multiverse. In this picture, inflation operates continuously throughout infinite space, creating an ever-expanding network of causally disconnected cosmic domains without any center or boundary. Our universe becomes one bubble in an infinite foam of cosmic regions undergoing independent evolution. The observational predictions of inflation include specific patterns in cosmic microwave background temperature and polarization fluctuations that encode information about inflatoned field properties and inflation dynamics. The scalar fluctuations create temperature variations with nearly scale-invariant power spectra, while tensor fluctuations from gravitational waves create characteristic polarization patterns that could provide direct evidence for inflationary expansion. Recent observations have confirmed many inflationary predictions while constraining inflatoned field properties with increasing precision. The Planck satellite's measurements of cosmic microwave background anisotropies are consistent with simple slow-roll inflation models while ruling out many alternative scenarios. The detection of primordial gravitational waves through B-mode polarization measurements would provide definitive confirmation of inflationary expansion. String theory approaches to inflation attempt to identify the inflatoned field with specific string theory objects like moduli fields or brane dynamics. These models connect inflation to fundamental physics while potentially explaining why inflation occurs and how it relates to other aspects of particle physics and quantum gravity. String inflation models make distinctive observational predictions that might be testable through future cosmic microwave background measurements. The multiverse implications of eternal inflation raise fundamental questions about the relationship between our observable cosmic domain and the larger inflating space within which it exists. If inflation creates infinite numbers of causally disconnected cosmic regions, then our universe's properties might be determined by anthropic selection rather than fundamental physics, with observers only existing in cosmic domains where physical parameters permit the development of complex structure and life. Alternative inflation models include scenarios where inflation is driven by multiple fields, where inflation occurs in extra dimensions, or where inflation is replaced by other mechanisms for creating cosmic uniformity. Ekperiodic and cyclic cosmologies propose that cosmic uniformity results from contracting phases that precede expansion, while string gas cosmology suggests that uniformity emerges from string theory dynamics in the early universe. The quantum foundations of inflation involve sophisticated treatments of quantum field theory and curved spacetime that push theoretical physics to its limits. The calculation of quantum fluctuation amplitudes during inflation requires understanding how quantum fields behave in rapidly expanding spacetime, including back-reaction effects where quantum fluctuations influence the background expansion rate. Future theoretical developments in inflation include attempts to connect inflationary models to more fundamental theories of quantum gravity, investigations of inflation's relationship to dark energy and cosmic acceleration, and studies of how inflation might lead to testable predictions for high-energy physics beyond standard model. But cosmic inflation raises profound questions about the nature of space and causality in an exponentially expanding universe. How does inflation create space and matter from vacuum fluctuations without violating conservation laws? What determines when and where inflation begins and ends? How do we understand cosmic evolution in scenarios where inflation operates eternally throughout infinite space, creating infinite numbers of causally disconnected cosmic domains? Chapter 6. Dark Matter's Hidden Democracy. Invisible throughout the universe, comprising 27% of cosmic energy density, yet interacting only through gravitational forces. Dark matter creates the hidden scaffolding that guides galaxy formation while maintaining perfect democratic distribution across cosmic scales. This mysterious component reveals its presence through gravitational effects that show no evidence for cosmic centers or preferred locations, instead demonstrating that even invisible matter participates in the centerless architecture that defines cosmic structure on the largest observable scales. The discovery of dark matter began with observations of galaxy rotation curves that revealed orbital velocities inconsistent with the gravitational effects of visible matter alone. In the 1970s, Vera Rubin and Ken Ford measured stellar velocities in spiral galaxies and found that stars in galactic outskirts orbit much faster than predicted by Newton's laws applied to observe stellar and gas masses. These high orbital velocities require additional gravitational mass distributed throughout galactic halos in ways that cannot be explained by any form of ordinary matter. Galaxy cluster dynamics provided additional evidence for dark matter through measurements of cluster masses using multiple independent techniques. The velocities of galaxies orbiting within massive clusters indicate total cluster masses much larger than the combined masses of visible galaxies. Gravitational lensing observations, which measure cluster masses through their deflection of background galaxy images, confirm these dynamical mass measurements while revealing that most cluster mass exists in invisible form. The cosmic distribution of dark matter, mapped through gravitational lensing surveys and computer simulations, reveals large-scale structure that mirrors the distribution of visible matter while showing no evidence for overall cosmic asymmetries or central concentrations. Dark matter forms filamentary networks connecting galaxy clusters while avoiding cosmic voids, creating three-dimensional scaffolding that guides ordinary matter's gravitational collapse into galaxies and larger structures. This cosmic web of dark matter demonstrates remarkable uniformity when averaged over sufficiently large scales, with statistical properties that remain constant across different regions of the observable universe. Large-scale structure surveys mapping millions of galaxies reveal clustering patterns that match theoretical predictions for centerless dark matter distributions, confirming that dark matter participates in the same homogeneous and isotropic cosmic expansion that characterizes visible matter. The nature of dark matter remains one of cosmology's greatest mysteries, with theoretical proposals ranging from weakly interacting massive particles, WIMPs, to axions, sterile neutrinos, and more exotic possibilities. Direct detection experiments have yet to identify dark matter particles despite decades of increasingly sensitive searches, while particle accelerator experiments have found no evidence for dark matter production in high-energy collisions. Computer simulations of dark matter structure formation, based on the gravitational clustering of collisionless particles in expanding spacetime, successfully reproduce observed large-scale structure patterns while making detailed predictions for dark matter density profiles within galactic halos. These simulations confirm that dark matter's gravitational effects alone are sufficient to explain cosmic structure formation without requiring any central organizing principles. The Millennium Simulation and other large-scale structure calculations follow the gravitational evolution of billions of dark matter particles from early cosmic epochs through the present day, revealing how tiny density fluctuations grow into the cosmic web through purely gravitational processes. These simulations demonstrate that dark matter structure formation operates according to centerless gravitational dynamics that preserve statistical uniformity across cosmic scales. Modified gravity theories attempt to explain galaxy rotation curves and cluster dynamics without invoking dark matter by proposing that gravitational physics itself differs from Einstein's general relativity on galactic and cosmic scales. Modified Newtonian dynamics, MOND, and other alternative gravity theories can explain some galactic observations but struggle to match the full range of cosmological evidence that supports dark matter's existence. The cosmic microwave background radiation encodes detailed information about dark matter through its influence on acoustic oscillations in the early universe plasma. Dark matter's gravitational effects modify the propagation of sound waves through the pre-recombination universe, creating characteristic signatures in temperature and polarization fluctuations that enable precise measurements of dark matter density and clustering properties. These cosmic microwave background measurements, combined with observations of type Ia supernova and baryon acoustic oscillations, establish a concordance cosmological model where dark matter comprises approximately 27% of cosmic energy density while being distributed uniformly throughout space on scales larger than galaxy clusters. This cosmic accounting confirms that dark matter participates in centerless cosmic expansion while dominating gravitational structure formation. The relationship between dark matter and ordinary matter during cosmic evolution reveals important aspects of how centerless expansion permits local structure formation while maintaining global uniformity. While cosmic expansion drives galaxies apart on the largest scales, dark matter's gravitational effects enable local gravitational collapse that creates galactic structures within the expanding cosmic background. Dark matter's collisionless nature allows it to form stable gravitational structures that resist disruption by electromagnetic processes affecting ordinary matter. This enables dark matter halos to maintain their structural integrity, while ordinary matter dissipates energy through electromagnetic interactions and collapses into dense stellar systems at halo centers. The resulting galaxy formation process preserves dark matter's uniform cosmic distribution while concentrating ordinary matter into visible galactic components. Gravitational lensing observations provide the most direct evidence for dark matter's spatial distribution by measuring how dark matter deflects light from background sources. Weak lensing surveys mapping subtle distortions in galaxy shapes across large sky areas reveal dark matter distributions that match theoretical predictions for centerless structure formation. while strong lensing observations of galaxy clusters confirm detailed dark matter density profiles predicted by cosmological simulations. The Bullet Cluster and other merging galaxy clusters provide dramatic demonstrations of dark matter's existence through observations of separated dark matter and ordinary matter components during cluster collisions. When galaxy clusters collide, ordinary matter interacts electromagnetically and becomes heated and slowed, while dark matter continues moving according to purely gravitational dynamics. This separation reveals dark matter's spatial distribution directly through gravitational lensing measurements. Future dark matter research will combine improved direct detection experiments, indirect detection, searches for dark matter annihilation or decay signatures, and precision cosmological measurements to constrain dark matter properties while testing whether dark matter's cosmic distribution continues to show centerless uniformity on ever larger scales. The Large Synoptic Survey Telescope and other next-generation surveys will map dark matter distributions across unprecedented cosmic volumes while searching for deviations from perfect statistical uniformity that might reveal new physics operating on cosmic scales. These measurements will test whether dark matter maintains its democratic distribution as observations push toward the largest observable scales. Particle physics experiments, including the Large Hadron Collider, continue searching for evidence of dark matter production in high-energy collisions, while space-based detectors look for gamma rays, neutrinos, and other signatures of dark matter interactions in cosmic environments. Underground detectors with increasing sensitivity probe direct interactions between dark matter particles and ordinary matter nuclei. The relationship between dark matter and dark energy represents one of cosmology's deepest mysteries, with both components showing uniform cosmic distributions while influencing cosmic evolution through different mechanisms. Dark matter dominates gravitational structure formation, while dark energy drives cosmic acceleration, suggesting that cosmic evolution results from competition between gravitational collapse and cosmic expansion, without any central coordination. Alternative dark matter scenarios include self-interacting dark matter that experiences forces beyond gravity, primordial black holes formed in the early universe, and composite dark sectors containing multiple types of dark particles with complex interactions. Each possibility makes different predictions for dark matter's cosmic distribution and clustering properties that can be tested through observations. The quantum nature of dark matter, whether consisting of fundamental particles or composite objects, connects dark matter physics to theories of quantum gravity and the fundamental structure of spacetime. If dark matter consists of ultralight particles like axions, quantum mechanical effects might influence dark matter clustering on galactic scales while preserving uniform distributions on cosmic scales. But dark matter's hidden democracy raises fundamental questions about the relationship between visible and invisible cosmic components. How does dark matter maintain such uniform cosmic distribution while enabling local structure formation? What determines dark matter's interaction properties that allow it to form stable structures while remaining invisible? How does dark matter connect to the fundamental physics underlying cosmic expansion and the universe's centerless architecture? Chapter 7. Dark Energy's Democratic Acceleration. The most mysterious component in the universe, dark energy, comprises 68% of cosmic density while driving accelerated expansion that operates identically from every location and in every direction throughout space, representing the ultimate expression of cosmic democracy, where no region enjoys privileged access to the fundamental force shaping cosmic evolution. This invisible energy pervades every cubic centimeter of space with constant density, creating repulsive gravitational effects that accelerate cosmic expansion while maintaining perfect homogeneity and isotropy across scales spanning billions of light years. The discovery of cosmic acceleration in 1998 represented one of the most shocking revelations in the history of astronomy. overturning the fundamental assumption that gravitational forces would gradually slow cosmic expansion over time. Two independent research teams studying Type Ia supernova at cosmological distances found that these standard candles appeared dimmer than expected in a decelerating universe, indicating that cosmic expansion has been speeding up rather than slowing down for approximately the past 6 billion years. Type Ia supernova serve as cosmic distance indicators because they result from thermonuclear explosions of white dwarf stars that reach the same critical mass regardless of their location or cosmic epoch. This standardized explosion mechanism creates supernova with nearly identical peak luminosities, enabling astronomers to measure cosmic distances by comparing observed brightness with known intrinsic luminosity. When combined with redshift measurements indicating recession velocity, these distance brightness relationships reveal cosmic expansion history. The supernova observations revealed cosmic expansion curves inconsistent with universes containing only matter and radiation, which would decelerate due to gravitational attraction between cosmic components. Instead, the data required additional cosmic energy with negative pressure that creates repulsive gravitational effects, accelerating cosmic expansion against gravitational deceleration. This mysterious energy component was dubbed energy due to its invisible nature and unknown physical properties. Subsequent observations using diverse cosmic distance indicators have confirmed cosmic acceleration while measuring dark energy as properties with increasing precision. Baryon acoustic oscillations, sound waves frozen into large-scale structure at recombination, provide standard rulers for measuring cosmic expansion across multiple cosmic epochs. Cosmic microwave background observations constrain cosmic geometry and expansion dynamics during early cosmic evolution. Each independent measurement confirms accelerated expansion driven by uniformly distributed dark energy. The cosmological constant represents the simplest theoretical explanation for dark energy, corresponding to a constant energy density associated with empty space itself. In this interpretation, vacuum energy creates repulsive gravitational effects that remain constant as space expands, maintaining fixed energy density through the continuous creation of vacuum energy in newly created spatial volume. This vacuum energy hypothesis connects dark energy to quantum field theory as prediction of zero-point energy in empty space. However, naive calculations of vacuum energy density using quantum field theory yield results larger than observed dark energy density by factors exceeding 10^120, creating the cosmological constant problem, the largest discrepancy between theoretical prediction and observational measurement in physics. This enormous disagreement suggests that either our understanding of vacuum energy is fundamentally flawed or that unknown physics cancels most vacuum energy contributions to cosmic dynamics. Alternative dark energy models propose that cosmic acceleration results from dynamic scalar fields that evolve over cosmic time, creating equation of state parameters that differ from the cosmological constants W equals -1 value. Quintessence models use slowly evolving scalar fields with negative pressure, but W greater than -1, while phantom energy models invoke -1 scenarios that would eventually lead to Big Rip cosmic endings, where expansion acceleration becomes infinite. The spatial distribution of dark energy shows no evidence for clustering, preferred directions, or central concentrations, instead maintaining constant density throughout space regardless of local matter, distributions, or gravitational field strengths. This uniform distribution distinguishes dark energy from ordinary matter and dark matter, which cluster gravitationally and show spatial variations correlated with cosmic structure. Dark energy's uniformity preserves cosmic homogeneity and isotropy while driving accelerated expansion. Recent surveys mapping cosmic acceleration across different cosmic epochs and spatial scales have confirmed that dark energy operates democratically throughout space and time. The Dark Energy Survey, studying hundreds of millions of galaxies across cosmic history, finds consistent evidence for uniform cosmic acceleration with no detectable variations across different sky regions or distance ranges. These observations confirm that dark energy maintains the same properties regardless of local cosmic environment. The relationship between dark energy and cosmic expansion reveals fundamental aspects of how centerless acceleration operates throughout the universe. Unlike conventional forms of energy that dilute as space expands, dark energy maintains constant density during expansion, ensuring that its gravitational effects strengthen relative to diluting matter and radiation. This behavior naturally explains why cosmic acceleration began approximately 6 billion years ago when dark energy density exceeded matter density. Dark energy's negative pressure creates repulsive gravitational effects through Einstein's general relativity, where pressure contributes to gravitational source terms alongside energy density. The combination of positive energy density and negative pressure in dark energy creates net repulsive gravitational effects that accelerate cosmic expansion while preserving the geometric relationships that maintain centerless expansion dynamics. The future evolution of cosmic acceleration depends on dark energy's long-term behavior, which remains observationally unconstrained beyond the recent cosmic past. If dark energy represents a true cosmological constant, cosmic acceleration will continue indefinitely, eventually driving exponential expansion that separates all cosmic structures beyond mutual observational contact. This scenario leads to cosmic loneliness, where each galaxy becomes isolated within its own observable universe. Alternative dark energy scenarios predict different cosmic futures, including Big Rip endings where phantom energy drives infinite expansion acceleration, cyclic cosmologies where dark energy eventually reverses sign and causes cosmic recollapse, or decay scenarios where dark energy density decreases over time and allows gravitational deceleration to resume. Each possibility depends on dark energy's fundamental nature and governing physics. The measurement of dark energy properties continues to improve through increasingly sophisticated observational programs using multiple complementary techniques. The Euclid Space Telescope and other next-generation surveys will measure cosmic acceleration across larger volumes and longer cosmic epochs while searching for evolution in dark energy's equation of state that would reveal its fundamental nature. Gravitational wave astronomy provides entirely new approaches to measuring cosmic expansion and dark energy through gravitational wave propagation effects and standard siren distance measurements. The LIGO-Virgo detection of neutron star mergers enables independent measurements of cosmic distances that complement electromagnetic observations while potentially revealing gravitational wave propagation effects sensitive to dark energy properties. The connection between dark energy and fundamental physics remains one of the deepest unsolved problems in cosmology and particle physics. Attempts to explain dark energy through modified gravity theories, extra dimensions, or quantum field theory mechanisms have not yet produced compelling explanations that match observational constraints while solving the cosmological constant problem. String theory approaches to dark energy propose that cosmic acceleration results from dynamics of extra dimensions, brane configurations or moduli fields that create effectively four-dimensional dark energy while connecting to fundamental string theory physics. These models attempt to explain why dark energy has the specific density and equation of state observed today, while potentially predicting future evolution. The anthropic principle suggests that dark energy density might be constrained by requirements for cosmic structure formation and biological evolution, with observers only existing in cosmic regions where dark energy permits galaxy formation while avoiding premature cosmic acceleration that would prevent structure development. This selection effect might explain dark energy's observed properties through environmental rather than fundamental physics. Laboratory searches for dark energy effects have attempted to detect fifth forces, chameleon mechanisms, or other signatures of dark energy physics operating in terrestrial environments. These experiments probe whether dark energy interacts with ordinary matter through forces beyond gravity, while testing theoretical models that predict environment-dependent dark energy properties. The philosophical implications of dark energy's democratic acceleration challenge assumptions about cosmic purpose, direction, and ultimate fate. If dark energy drives eternal acceleration toward cosmic isolation, this suggests a universe evolving toward maximum entropy and minimum complexity, rather than toward greater organization and structure. The cosmic democracy of dark energy ensures that no location receives preferential treatment, while cosmic evolution proceeds toward increasingly dilute and disconnected futures. But dark energy's uniform acceleration raises fundamental questions about the nature of space, energy, and cosmic evolution. How does dark energy maintain constant density during cosmic expansion without violating conservation laws? What determines dark energy's specific equation of state and energy density? How does dark energy connect to quantum mechanics, gravity, and the other fundamental forces that govern cosmic physics? Chapter 8. The Observable Universe Paradox. Every observer throughout the cosmos sits at the exact center of their own observable universe, a perfect sphere containing all the light that has had time to reach them since cosmic transparency began 13.8 billion years ago. This creates a profound paradox. If everyone sees themselves at the center of their own cosmic sphere, how can we claim the universe has no center? The resolution reveals deep truths about the relationship between observational limitations, cosmic geometry, and the distinction between local perspectives and global cosmic structure. The observable universe represents a fundamental limitation imposed by the finite speed of light combined with the finite age of cosmic transparency. Since electromagnetic radiation can only travel at light speed, there exists a maximum distance from which light could have reached any observer during the approximately 13.8 billion years since the cosmic microwave background was emitted. This creates a cosmic horizon that defines the boundary of observable space for every conscious being throughout the universe. The current radius of the observable universe extends approximately 46.5 billion light-years due to cosmic expansion effects that have stretched space while ancient photons traveled toward Earth. Although these photons began their journey 13.8 billion years ago, the galaxies that emitted them have since receded to much greater distances as space continued expanding. This expansion means that the most distant observable galaxies now exist approximately 46.5 billion light-years away, creating observable universes much larger than naive calculations might suggest. Every observer throughout the cosmos possesses their own observable universe with identical radius, but centered on their specific location. An alien astronomer in the Andromeda Galaxy sees themselves surrounded by a sphere of observable space extending 46.5 billion light-years in every direction from their position. Most of their observable universe consists of cosmic regions that we cannot observe from Earth, while most of our observable universe lies beyond their cosmic horizon. This multiplication of cosmic perspectives creates the observable universe paradox. Each observer legitimately claims to occupy the center of the observable cosmos, while seeing essentially the same large-scale cosmic structure. The cosmic microwave background appears the same from every location. Galaxy recession follows Hubble's law for every observer, and large-scale structure maintains statistical uniformity regardless of observational perspective. The resolution begins with recognizing that observable universe boundaries represent observational limitations rather than physical cosmic structures. The cosmic horizon that defines our observable universe boundary has no special physical significance. It simply marks the distance beyond which light has not yet had time to reach us. Galaxies beyond our cosmic horizon continue existing and evolving according to the same physical laws that govern cosmic evolution within our observable region. This understanding transforms the observable universe from a cosmic structure into an informational boundary that varies for different observers while revealing the same underlying cosmic architecture. Every observer sees statistical isotropy and homogeneity within their observable universe because these represent genuine properties of cosmic structure rather than artifacts of particular observational locations. The cosmic principle of mediocrity suggests that our observable universe provides a representative sample of cosmic structure on the largest scales, meaning that cosmic properties derived from our observations apply throughout infinite space beyond our observational reach. Large-scale surveys mapping galaxy distributions across billions of light-years support this assumption by revealing statistical uniformity that appears to extend indefinitely beyond current observational limits. The relationship between local observational constraints and global cosmic structure becomes particularly important when considering cosmic curvature and topology. Our observable universe could represent a tiny fraction of a much larger closed cosmic space that curves back on itself, an infinite flat space that extends forever, or a hyperbolic space with infinite negative curvature. Current observations cannot distinguish between these possibilities because cosmic curvature effects become significant only on scales comparable to or larger than our observable universe. Eternal inflation models predict that our observable universe represents an infinitesimally small fraction of an eternally inflating multiverse where inflation continues indefinitely in most regions while ending locally to create causally disconnected cosmic domains like our own. In this scenario, our observable universe provides information about local cosmic properties while revealing nothing about the infinite larger context within which it exists. The anthropic principle complicates interpretation of observable universe properties by suggesting that we necessarily observe cosmic parameters compatible with our existence rather than randomly selected cosmic properties. If inflation creates cosmic domains with varying physical parameters, then observers can only evolve in regions with parameters suitable for complexity and life, potentially biasing our observations toward atypical cosmic properties. Future cosmic evolution will modify observable universe properties as cosmic expansion continues carrying distant galaxies beyond our cosmic horizon while bringing previously unobservable regions into view. However, cosmic acceleration driven by dark energy means that the number of galaxies within our observable universe will eventually begin decreasing as expansion carries them beyond the receding cosmic horizon faster than new regions become observable. In the far future dominated by dark energy, cosmic acceleration will create exponentially expanding space that eventually isolates every galaxy within its own causally disconnected cosmic domain. This cosmic loneliness means that future observers will see apparently empty universes despite existing within the same infinite cosmic space that currently appears filled with billions of galaxies. Advanced civilizations might develop techniques for observing beyond conventional cosmic horizons through gravitational wave astronomy, neutrino detection, or other messenger particles that can traverse cosmic distances unimpeded by electromagnetic opacity. These alternative observation windows might eventually reveal cosmic structure extending far beyond electromagnetic cosmic horizons while testing assumptions about cosmic uniformity on larger scales. The search for cosmic topology signatures attempts to detect whether our observable universe exists within a finite cosmic space that curves back on itself through non-trivial topological connections. If space possesses dodecahedral, toroidal, or other topological structures smaller than our observable universe, then we should observe correlated patterns in cosmic microwave background radiation or galaxy distributions that reveal the cosmic space's finite size and shape. Precision measurements of cosmic parameters using observable universe data have achieved extraordinary accuracy through combining multiple independent observational techniques. The cosmic microwave background, type Ia supernova, baryon acoustic oscillations, and other cosmic probes yield consistent parameter values that define the lambda CDM concordance cosmological model, with uncertainties approaching 1% for many cosmic parameters. These measurements assume that our observable universe provides unbiased information about global cosmic properties, an assumption that becomes increasingly difficult to test as observations approach the cosmic horizon. Alternative cosmic models that predict systematic variations in cosmic properties across scales larger than our observable universe could potentially explain observed cosmic fine-tuning through selection effects rather than fundamental physics. The philosophical implications of observable universe limitations extend to fundamental questions about the relationship between observational knowledge and cosmic reality. If cosmic structure extends infinitely beyond our observational reach, then most cosmic reality remains permanently inaccessible to direct observation, raising questions about the epistemological foundations of cosmology and the limits of empirical knowledge. The development of cosmic archaeology techniques attempts to extract information about cosmic regions and epochs beyond direct observational access to indirect signatures preserved in observable cosmic phenomena. Gravitational wave backgrounds, primordial nucleosynthesis products, and cosmic microwave background patterns might encode information about cosmic structure, extending far beyond electromagnetic cosmic horizons. Future theoretical developments might identify fundamental principles that constrain cosmic properties beyond observational verification, potentially enabling deductive understanding of infinite cosmic structure through mathematical necessity rather than empirical observation. String theory, quantum gravity, and other fundamental physics approaches attempt to derive cosmic parameters from first principles rather than observational fitting. But the observable universe paradox raises fundamental questions about the nature of cosmic knowledge and the relationship between local observations and global cosmic structure. How do we distinguish between observational artifacts and genuine cosmic properties when our observations are necessarily limited to tiny fractions of infinite space? What does cosmic homogeneity and isotropy mean if we can only observe infinitesimal samples of cosmic structure? How do we understand cosmic evolution when most cosmic history unfolds beyond our observational reach? Chapter 9. Beyond the Horizon. At the edge of our observable universe lies one of the most profound boundaries in physics, the cosmic horizon beyond which no light has yet had time to reach us since the universe became transparent. But this horizon doesn't mark the edge of cosmic space itself. Instead, it represents the beginning of infinite cosmic realms that continue expanding, evolving, and potentially harboring galaxies, stars, and life completely beyond our observational reach. Understanding what lies beyond the horizon reveals the ultimate democracy of cosmic structure, where infinite space operates according to identical physical laws while remaining forever hidden from direct observation. The cosmic horizon exists approximately 46.5 billion light-years from Earth, marking the distance to regions whose light began traveling toward us at the moment of cosmic recombination 13.8 billion years ago. Beyond this horizon, galaxies and cosmic structures continue existing and evolving according to the same physical laws that govern cosmic evolution within our observable region. But their light has not yet had sufficient time to traverse the intervening cosmic distances to reach our telescopes. The nature of space beyond the cosmic horizon depends fundamentally on cosmic topology and the global structure of cosmic geometry. If space extends infinitely in all directions, as current observations suggest, then cosmic structure continues indefinitely beyond our observational reach, with galaxy distributions maintaining the same statistical properties observed within our cosmic neighborhood. This infinite space contains infinite numbers of galaxies, stars, planets, and potentially infinite instances of every possible cosmic structure. Cosmic inflation provides the theoretical framework for understanding how structure beyond the cosmic horizon relates to observable cosmic properties. If inflation operated throughout infinite space during the universe's first fraction of a second, then quantum fluctuations were stretched to cosmic scales simultaneously throughout infinite spatial volumes, creating statistical uniformity that extends far beyond any individual cosmic horizon. This inflationary homogenization ensures that unobservable cosmic regions possess the same statistical properties as observable space. The cosmic microwave background radiation provides indirect evidence about structure beyond the cosmic horizon through correlations that exist between regions, currently separated by distances larger than the horizon scale at recombination. These correlations require that currently unobservable regions were in causal contact before. Inflation stretched them beyond mutual communication, providing circumstantial evidence that unobservable space possesses similar properties to observable regions. Advanced theoretical models predict specific relationships between observable and unobservable cosmic structure, based on the assumption that physical laws operate identically throughout infinite space. Computer simulations of cosmic structure formation can be extrapolated beyond observational limits to predict statistical properties of galaxy distributions, dark matter clustering, and cosmic evolution in regions that remain permanently beyond observational verification. The multiverse implications of eternal inflation suggest that space beyond our cosmic horizon might contain not only more of the same cosmic structure, but also regions where cosmic evolution has proceeded differently due to varying initial conditions or possibly different physical parameters. If inflation creates causally disconnected cosmic domains with different properties, then unobservable space might harbor cosmic regions with alternative physics, different fundamental constants, or exotic forms of matter and energy. Anthropic selection effects could explain fine-tuned cosmic parameters through the existence of infinite cosmic regions with varying physical properties beyond our observational reach. In this scenario, observers can only evolve in cosmic domains with parameters suitable for complexity and life, making our observed cosmic properties unrepresentative of typical conditions throughout infinite space. The quantum mechanical foundations of cosmic structure suggest that space beyond the cosmic horizon participates in universal quantum entanglement networks that connect all cosmic regions through non-local quantum correlations. If cosmic inflation stretched quantum entanglement to cosmic scales, then unobservable cosmic regions might remain quantum mechanically connected to observable space through correlations that transcend classical causal limitations. Future cosmic evolution will gradually bring currently unobservable regions within our cosmic horizon as light from increasingly distant sources finally reaches Earth. However, cosmic acceleration driven by dark energy means that this expansion of observable space will eventually reverse, with accelerating expansion carrying cosmic structures beyond our horizon faster than new regions become observable. The far future evolution of cosmic horizons creates scenarios where observable space becomes increasingly empty as dark energy drives exponential expansion that isolates every galaxy within its own causally disconnected observable universe. This cosmic loneliness represents the ultimate consequence of centerless expansion, where democratic cosmic structure eventually leads to complete observational isolation for every conscious observer. Advanced civilizations might develop techniques for observing beyond electromagnetic cosmic horizons through gravitational wave detection, high-energy neutrino astronomy, or other messenger particles that can penetrate cosmic distances unaffected by electromagnetic opacity. These alternative observation windows might eventually reveal cosmic structure extending beyond conventional horizon limitations while testing theoretical predictions about infinite space. The search for cosmic topology signatures attempts to determine whether space beyond the cosmic horizon eventually connects back to currently observable regions through non-trivial topological relationships. If cosmic space possesses finite volume with complex topology, then we might observe multiple images of the same cosmic structures viewed from different directions, potentially revealing the global shape and size of cosmic space. Gravitational effects from structure beyond the cosmic horizon might create detectable influences on cosmic evolution within observable space through large-scale gravitational coherence effects. Bulk flows, cosmic dipole anisotropies, or other systematic motions within observable space might reflect gravitational influences from massive structures beyond current observational limits. The cosmic web of dark matter and large-scale structure likely extends continuously beyond the cosmic horizon, creating filamentary networks and cluster formations that follow the same statistical patterns observed within our cosmic neighborhood. Computer simulations suggest that this cosmic web continues indefinitely throughout infinite space while maintaining statistical uniformity on sufficiently large scales. Primordial gravitational wave backgrounds carry information about cosmic conditions during inflation that might encode details about space beyond the cosmic horizon through gravitational wave correlations that extend across currently unobservable distances. Future gravitational wave detectors might detect these primordial signals while revealing information about cosmic structure formation throughout infinite space. The relationship between cosmic complexity and infinite space suggests that every possible cosmic structure and evolutionary pathway that can exist within the constraints of physical law must exist somewhere within infinite space beyond our cosmic horizon. This includes infinite variations of galactic structures, stellar systems, planetary configurations, and potentially biological evolution leading to infinite instances of life and intelligence. Digital physics approaches suggest that cosmic evolution might be fundamentally computational, with infinite space containing infinite computational resources that enable every possible information processing pattern to exist somewhere within the cosmic computer. This perspective treats consciousness and life as computational patterns that must occur infinitely throughout infinite space while remaining mostly beyond observational detection. The philosophical implications of infinite space beyond the cosmic horizon challenge assumptions about uniqueness, significance, and the relationship between local experience and cosmic reality. If infinite space contains infinite variations of every possible cosmic structure, then our observable universe and everything within it represents infinitesimal fractions of much larger patterns that extend throughout infinite reality. The epistemological challenges of understanding infinite space raise fundamental questions about the nature of scientific knowledge when most reality remains permanently beyond empirical verification. How do we validate theoretical predictions about infinite space that can never be directly tested? What does scientific understanding mean when applied to cosmic realms that transcend observational limits? Future developments in fundamental physics might identify mathematical principles or symmetries that constrain cosmic structure throughout infinite space independent of observational verification. String theory, loop quantum gravity, and other approaches to quantum gravity attempt to derive cosmic properties from first principles rather than empirical fitting, potentially enabling deductive knowledge about infinite cosmic structure. But understanding space beyond the horizon raises the deepest questions about cosmic democracy and the nature of existence itself. If identical physical laws operate throughout infinite space, creating infinite instances of every possible cosmic structure, what does this mean for individuality, purpose, and significance? How do we understand our place within infinite cosmic democracy, where every possible existence occurs infinitely throughout space that extends forever beyond our observational reach. Chapter 10. The Geometry of Infinity. The shape of cosmic space itself determines whether the universe extends infinitely in all directions or curves back on itself in exotic topological configurations that make cosmic center a meaningless concept regardless of cosmic size. Current observations suggest that space is geometrically flat to extraordinary precision, implying infinite extent where every point can equally claim to be the cosmic center, because infinite space has no center, no edges, and no preferred locations within its endlessly democratic expanse. The mathematical description of cosmic geometry uses the framework of differential geometry to characterize how space curves in response to matter and energy distributions. Einstein's field equations relate spacetime curvature to cosmic energy density through the stress-energy tensor, enabling precise calculations of cosmic geometry based on observational measurements of cosmic matter and energy content. These geometric relationships determine whether cosmic space is flat, spherically curved, or hyperbolically curved on the largest scales. Flat cosmic geometry, corresponding to Euclidean space extended to cosmic scales, requires critical cosmic density where gravitational attraction exactly balances cosmic expansion kinetic energy. In flat space, parallel lines remain parallel across cosmic distances. The angles of cosmic triangles sum to 180 degrees, and the ratio of cosmic circles' circumferences to their diameters equals pi. This geometric flatness enables infinite cosmic extension, where space continues indefinitely in all directions without curving back on itself. Spherically curved cosmic geometry, corresponding to the three-dimensional analog of a sphere's surface, requires cosmic density above the critical value where gravitational attraction eventually overcomes cosmic expansion. In spherically curved space, parallel lines eventually converge. Cosmic triangles have angle sums exceeding 180 degrees, and cosmic circles have circumference to diameter ratios less than pi. This positive curvature creates finite cosmic volume that curves back on itself without boundaries or edges. Hyperbolically curved cosmic geometry, corresponding to saddle-shaped surfaces extended to 3 dimensions, requires cosmic density below the critical value where cosmic expansion overwhelms gravitational attraction. In hyperbolic space, parallel lines diverge. Cosmic triangles have angle sums less than 180 degrees, and cosmic circles have circumference to diameter ratios exceeding pi. This negative curvature creates infinite cosmic volume that extends indefinitely while curving away from itself in all directions. Current observational measurements of cosmic geometry, derived primarily from cosmic microwave background acoustic oscillation patterns, indicate that cosmic space is flat to within approximately 0.4% uncertainty. This geometric flatness corresponds to cosmic density, equaling the critical density to extraordinary precision, requiring fine-tuned relationships between matter density, dark energy density, and cosmic curvature that make cosmic geometry almost perfectly Euclidean. The implications of geometric flatness for cosmic infinity are profound, because flat space naturally extends infinitely in all directions without requiring special boundary conditions or edge effects. If space is truly flat and infinite, then cosmic structure continues indefinitely beyond our observational reach while maintaining the same statistical properties observed within our cosmic neighborhood. This infinite extension contains infinite numbers of galaxies, stars, and potentially infinite instances of every possible cosmic structure. Cosmic topology introduces additional geometric complexity by describing how space connects to itself through global topological relationships that can differ from local geometric properties. Even if space appears locally flat, it might possess non-trivial global topology that makes cosmic space finite through exotic connectivity patterns like toroidal, Klein bottle, or dodecahedral configurations that create finite cosmic volume within flat local geometry. The search for cosmic topology signatures focuses on detecting correlated patterns in cosmic microwave background radiation or galaxy distributions that would reveal non-trivial topological connections. If cosmic space has finite volume due to topological identification, then we should observe multiple images of the same cosmic regions viewed from different directions, creating characteristic correlations in temperature patterns or galaxy positions. Observational constraints on cosmic topology have ruled out most small-scale topological identifications while leaving open the possibility that cosmic space possesses large-scale topological structure comparable to or larger than our observable universe. Current data are consistent with either infinite flat space or finite flat space with topology scales exceeding observational limits, making cosmic infinitude observationally undetermined. The relationship between cosmic inflation and cosmic geometry provides theoretical insights into why space appears flat regardless of its initial curvature. Inflationary expansion stretches any initial curvature to negligible levels through exponential expansion factors that make curved space appear flat on scales much smaller than cosmic curvature radii. This inflationary flattening naturally explains observed geometric flatness while remaining consistent with the underlying curved or flat spatial topology. Eternal inflation models predict that infinite space undergoes continuing inflation in most regions while ending locally to create causally disconnected cosmic domains with potentially different geometric properties. This scenario suggests that our observable universe represents a flat geometric region within much larger inflating space that might possess different curvature properties in regions beyond our observational reach. The quantum mechanical foundations of cosmic geometry involve sophisticated treatments of quantum gravity effects that might modify classical geometric relationships at the Planck scale or during extreme cosmic epochs. Loop quantum gravity suggests that space itself might be quantized into discrete geometric units, while string theory proposes that cosmic geometry emerges from higher dimensional structures that transcend conventional geometric concepts. These quantum geometric effects might create discrete cosmic structure at microscopic scales while producing continuous geometric properties on macroscopic scales through statistical averaging over quantum geometric fluctuations. The resulting emergent geometry could appear classically flat while possessing underlying quantum structure that influences cosmic evolution through subtle quantum gravitational effects. The multiverse implications of cosmic geometry suggest that infinite space contains cosmic domains with all possible geometric configurations, including flat, curved, and topologically complex regions that evolve according to different geometric constraints. If inflation creates infinite spatial volume with varying geometric properties, then our observable flat geometry represents just one possibility within infinite geometric diversity. The anthropic principle might constrain observable cosmic geometry through requirements for cosmic structure formation and biological evolution, with observers only existing in cosmic domains where geometric properties permit galaxy formation, stellar nucleosynthesis, and planetary evolution, leading to complex chemistry and life. This selection effect might explain observed geometric flatness through environmental necessity rather than fundamental physics. Future observations using improved cosmic microwave background measurements, large-scale structure surveys, and gravitational wave astronomy will constrain cosmic geometry with increasing precision while searching for signatures of cosmic topology or geometric evolution that might reveal cosmic spatial structure beyond current observational limits. The philosophical implications of cosmic geometric infinity challenge assumptions about cosmic uniqueness, completeness, and the relationship between local geometric experience and global cosmic structure. If space extends infinitely with flat geometry, then every local geometric configuration that can exist within physical constraints must exist somewhere within infinite space, creating infinite geometric diversity within universal geometric democracy. The mathematical beauty of cosmic geometric flatness suggests deep connections between cosmic structure and fundamental mathematical principles that determine why space adopts geometric configurations compatible with infinite extension. The critical density relationships required for geometric flatness involve precise numerical relationships between cosmic parameters that might reflect underlying mathematical necessities rather than accidental cosmic conditions. The relationship between cosmic geometry and consciousness raises questions about how geometric properties influence the evolution of awareness and intelligence within cosmic structure. Different geometric configurations would create different gravitational environments, cosmic evolution patterns, and structure formation processes that might favor or inhibit the development of complexity and life throughout infinite space. The ultimate questions raised by cosmic geometric infinity extend to fundamental issues about mathematical reality and physical existence. If infinite flat space contains infinite instances of every possible geometric pattern and cosmic structure, does this make geometric patterns mathematical objects that exist independently of physical instantiation? What is the relationship between mathematical space and physical space when cosmic geometry appears to transcend any finite physical implementation? But contemplating the geometry of infinite cosmic space raises the deepest questions about existence itself. How do we understand identity, purpose, and significance within infinite geometric democracy, where every possible cosmic structure exists infinitely throughout flat space that extends forever? What does it mean to exist within infinite geometric reality, where the very concept of cosmic center becomes meaningless? Chapter 11. Living in a Centerless Cosmos. Coming to terms with cosmic centerlessness represents one of the most profound psychological and philosophical challenges in human history, forcing us to reconstruct our understanding of place, purpose, and significance within a universe where no location enjoys special status and every position can equally claim to be the cosmic center. This radical reorientation requires developing new frameworks for meaning and identity that transcend center-based thinking while embracing the ultimate democracy of cosmic structure, where significance emerges from participation rather than position. The psychological impact of cosmic centerlessness cannot be understated because human consciousness evolved within environments where centers provide essential organizing principles for navigation, social structure, and meaning-making. Our intuitive spatial cognition assumes hierarchical organization around central landmarks, territories with defined boundaries, and social groups with clear leadership structures. The discovery that cosmic structure operates without any analogous organizing principles challenges fundamental assumptions about how reality organizes itself. This cognitive dissonance between evolved psychological tendencies and cosmic reality creates what we might call cosmic vertigo, the disorienting recognition that familiar spatial categories like center, edge, inside, and outside have no meaning when applied to the universe as a whole. The comfortable assumption that we must be somewhere special within cosmic architecture dissolves into the recognition that every location throughout infinite space can make identical claims to cosmic centrality. The historical precedents for cosmic decentering provide some guidance for adapting to centerless reality, but the scale of adjustment required for true centerlessness exceeds previous transitions. The Copernican revolution displaced Earth from the cosmic center while preserving solar centrality. The recognition that the solar system occupies no special galactic position preserved galactic centrality. The discovery that our galaxy is one among billions preserved the assumption that cosmic structure must organize itself around some hierarchical principles. Cosmic centerlessness eliminates these psychological escape routes by revealing that no hierarchical organization exists on cosmic scales. There is no cosmic downtown, no universal center of mass, no preferred reference frame from which cosmic evolution proceeds. Every galaxy cluster, every cosmic filament, every region of cosmic void exists within the same democratic cosmic structure where no location enjoys ontological priority over any other. The philosophical implications extend beyond spatial disorientation to fundamental questions about cosmic purpose and direction. If the universe has no center, then cosmic evolution cannot be understood as progress towards central goals or development from peripheral origins towards central culminations. Instead, cosmic evolution operates simultaneously throughout infinite space, according to local physical processes that create complex structures without central coordination or universal teleology. This elimination of cosmic teleology challenges meaning-making frameworks that assume cosmic purpose or direction, requiring new approaches to significance that emphasize participation in cosmic processes rather than progress toward cosmic goals. The meaning of existence must emerge from engagement with local cosmic structure and evolution rather than from occupying special positions within universal hierarchies. The scientific worldview provides frameworks for understanding cosmic significance through participation in cosmic evolution, structure formation, and complexity development that transcend any need for central cosmic positions. Conscious beings represent cosmic structure achieving self-awareness, enabling the universe to contemplate its own properties and evolution through observers that emerge from cosmic processes themselves. This participatory cosmic significance suggests that consciousness serves essential cosmic functions by enabling local cosmic structure to achieve understanding, appreciation, and creative response to cosmic conditions. Rather than being peripheral accidents in an indifferent universe, conscious beings represent cosmic evolution, developing awareness of its own operations through information processing systems complex enough to contemplate cosmic structure. The democratic nature of cosmic structure means that these opportunities for cosmic participation exist throughout infinite space, wherever local conditions permit the development of complexity, life, and consciousness. Every location throughout the universe offers equal access to cosmic participation while contributing unique perspectives to cosmic self-understanding that develop through locally specific evolutionary pathways. The implications for human cosmic significance become positive rather than diminishing when viewed through frameworks emphasizing participation over position. Humanity's emergence represents cosmic structure in our local region, developing technological capabilities for cosmic observation, space exploration, and potentially cosmic communication with other conscious beings throughout infinite space. Our cosmic investigations contribute to cosmic self-understanding while potentially connecting to similar investigations throughout infinite cosmic democracy. The development of cosmic communication technologies might enable connections with conscious beings throughout infinite space, creating networks of cosmic intelligence that transcend any individual cosmic location while enabling collaborative cosmic understanding that spans cosmic scales. These communication networks would operate democratically without central coordination while enabling shared cosmic investigation and potentially mutual assistance in cosmic exploration. Space exploration and cosmic engineering represent extensions of cosmic participation that could eventually enable human involvement in cosmic structure formation, star system engineering, and potentially cosmic evolution guidance on local scales. Rather than seeking cosmic centrality, advanced human civilization might focus on maximizing cosmic participation through technological capabilities that enable deeper engagement with cosmic processes. The aesthetic implications of cosmic centerlessness reveal new forms of cosmic beauty based on symmetry, uniformity, and democratic structure rather than hierarchical organization around cosmic centers. The extraordinary homogeneity and isotropy of cosmic structure on large scales represents a form of cosmic elegance that transcends any possible center-based organization while creating infinite opportunities for local complexity and diversity. The mathematical beauty of centerless cosmic structure suggests deep connections between cosmic organization and fundamental mathematical principles that operate democratically throughout infinite space. The precise physical constants, geometric relationships, and dynamical processes that enable cosmic complexity represent mathematical necessities rather than accidental arrangements, making cosmic participation in mathematical beauty accessible throughout infinite space. The spiritual implications of cosmic centerlessness challenge traditional religious frameworks based on cosmic hierarchy while opening new possibilities for spiritual understanding based on cosmic connection, participation, and appreciation. Rather than seeking special cosmic positions or central cosmic purposes, spiritual frameworks might emphasize harmonious participation in cosmic processes that transcend individual existence while remaining accessible through local engagement. The ethical implications extend to cosmic-scale moral considerations about humanity's responsibilities as conscious cosmic participants who have developed technological capabilities for influencing cosmic evolution on local scales. These responsibilities might include preserving cosmic complexity, enabling cosmic communication, and ensuring that technological development enhances rather than diminishes cosmic participation opportunities. The educational challenges of preparing future generations for life in a centerless cosmos require developing curricula that emphasize systems thinking, democratic participation, and appreciation for cosmic processes over hierarchical thinking, central authority, and competition for special positions. Understanding cosmic democracy becomes essential preparation for effective cosmic citizenship in infinite space. The psychological tools for adapting to cosmic centerlessness might include meditation practices that develop appreciation for present moment experience without requiring special cosmic positions, scientific education that emphasizes participation in cosmic understanding, and creative activities that engage with cosmic beauty and complexity through local artistic expression and technological development. The ultimate adjustment to cosmic centerlessness involves embracing the radical democracy of cosmic structure while finding meaning through participation rather than position, connection rather than centrality, and contribution rather than control. This represents a maturation of cosmic consciousness that transcends ego-centered thinking while enabling deeper appreciation for cosmic beauty, complexity, and the infinite opportunities for meaningful participation that exist throughout centerless space. But living consciously within cosmic democracy raises fundamental questions about identity, purpose, and cosmic responsibility. How do we understand individual significance within infinite cosmic structure, where every possible form of consciousness exists infinitely throughout space? What are our responsibilities as cosmic participants who have achieved technological capabilities for local cosmic influence? How do we find meaning and purpose within cosmic democracy that extends infinitely beyond any individual cosmic location? Throughout this exploration of cosmic centerlessness, we've uncovered perhaps the most profound truth about reality. The universe operates according to principles so democratically distributed that the very concept of cosmic center has no meaning whatsoever. From our initial intuitions about cosmic hierarchy through careful observations revealing universal recession, from Einstein's geometric revolution to the cosmic microwave background's perfect uniformity, every line of evidence points toward the same stunning conclusion. We live within infinite space, where every location can equally claim to be the cosmic center because no such center exists. We've seen how cosmic expansion operates without any central source or preferred direction, with space itself expanding uniformly throughout infinite volume while carrying galaxies along like markers embedded in stretching fabric. The recession patterns that initially seemed to place us at the cosmic center actually reflect centerless expansion that creates identical observational signatures for every observer throughout the universe, making apparent centrality a universal illusion rather than evidence for special position. The cosmic microwave background radiation has revealed the early universe's extraordinary uniformity, with temperature variations of only 10 parts per million across the entire sky, confirming that cosmic evolution proceeds democratically throughout space without central coordination or preferred regions. Cosmic inflation explains this uniformity through exponential expansion that stretched quantum fluctuations to cosmic scales while maintaining perfect homogeneity across regions far larger than any possible causal coordination could achieve. Dark matter and dark energy, comprising 95% of cosmic content, both demonstrate perfectly uniform distributions that show no evidence for cosmic centers or preferred locations. These invisible components shape cosmic evolution through gravitational effects and cosmic acceleration that operate identically throughout infinite space, ensuring that cosmic democracy extends to the fundamental forces governing cosmic structure and evolution. The geometry of infinite space itself eliminates any possibility for cosmic centers by extending indefinitely in all directions within flat spacetime that curves neither toward centers nor away from edges that don't exist. Every point in infinite space enjoys identical geometric relationships with cosmic structure, making mathematical centrality as meaningless as physical centrality in cosmic architecture that transcends any finite organizing principles. But perhaps the most profound realization is how this cosmic centerlessness transforms our understanding of significance and meaning within infinite space. Rather than diminishing human importance by removing us from special cosmic positions, centerless cosmos reveals that every location throughout infinite space offers equal opportunities for cosmic participation, understanding, and creative engagement with cosmic processes that operate democratically throughout reality. Your existence as a conscious observer represents cosmic structure achieving self-awareness in your local cosmic region, enabling the universe to contemplate its own properties through information processing systems that emerge from cosmic evolution itself. This participation in cosmic self-understanding represents genuine cosmic significance that depends on engagement rather than position, contribution rather than location within non-existent cosmic hierarchies. As you continue living after contemplating these cosmic truths, remember that you exist within infinite democratic space where every moment of consciousness contributes to cosmic self-understanding while participating in structure formation, complexity development, and potentially communication with conscious beings throughout infinite space. Your observations of cosmic beauty, scientific investigations, and creative responses to cosmic conditions represent the universe exploring its own infinite potential through locally specific evolutionary pathways. The cosmic democracy surrounding you extends infinitely beyond observational reach while maintaining identical physical laws and evolutionary processes that create infinite opportunities for cosmic participation. Every galaxy you observe, every star system that forms, every planet that develops complex chemistry represents cosmic democracy, generating infinite variations on cosmic themes that repeat throughout infinite space while remaining locally unique and meaningful. Your technological civilization represents cosmic matter achieving capabilities for space exploration, cosmic communication, and potentially cosmic engineering that could extend human participation in cosmic processes across multiple star systems and cosmic epochs. Rather than seeking cosmic centrality that doesn't exist, humanity might focus on maximizing cosmic participation through technologies that enable deeper engagement with cosmic structure and evolution. The centerless cosmos eliminates cosmic loneliness by revealing that consciousness emerges throughout infinite space, wherever local. Conditions permit complexity development, creating infinite communities of conscious beings, exploring cosmic structure through locally specific but universally connected investigations. Your cosmic curiosity connects you to infinite cosmic investigators throughout democratic space that extends forever in all directions. This cosmic perspective dissolves existential anxiety about cosmic significance, while opening infinite possibilities for meaningful cosmic engagement that transcend any individual lifespan or cosmic location. Every moment of cosmic appreciation, scientific discovery, or creative response to cosmic beauty contributes to infinite cosmic self-exploration, operating throughout space that has no center but infinite centers, no edge but infinite extensions, no hierarchy but perfect democracy. If you found yourself amazed by the discovery that the universe truly has no center, that cosmic democracy operates throughout infinite space, and that every location enjoys equal cosmic significance through participation rather than position, subscribe and give this video a thumbs up. Explore my investigation of the nature of cosmic infinity, where we delve deeper into the implications of infinite space for consciousness, meaning, and humanity's cosmic future. The universe has revealed its most fundamental architectural principle: perfect democracy, operating throughout infinite space, where no location receives preferential treatment and every position offers equal access to cosmic participation. We discovered that cosmic centers don't exist, not because we haven't found them yet, but because the mathematical structure of infinite reality makes cosmic centrality impossible in principle. You are not displaced from cosmic centrality. You participate in cosmic centrality that exists everywhere throughout infinite democratic space. Your consciousness represents the universe, achieving local self-awareness while contributing to infinite cosmic self-understanding, operating throughout centerless space that extends forever. In a cosmos without center, every moment is cosmic. Every location is significant. Every conscious being participates equally in infinite cosmic democracy that transcends any possible hierarchy, while enabling infinite opportunities for cosmic understanding, appreciation, and creative participation in reality itself. The universe has no center because infinite space makes every location the center. Welcome to Cosmic Democracy.